We continue part 3 on slide 24. Now, before we continue with defining the expansion path and obtaining our long run cost curves, we are going to look at figure 7.6a on the following slide. But before we do that, let's just look at the information that we are given. So we are given the information that a firm can hire labor, L, at $10 per hour. So that is the $10 per hour, the wage rate. L just represents how much labor may be used. Plus, we are told that the rental rate is $20 per hour. So they could hire units of capital at a rental rate of $20 per hour. So we have our input prices, and from this information, we could derive our ISO cost line. As you can see, you've got C is equal to your $10 times L plus your $20 per hour for your rental rate times K. C, which is your total cost, is going to depend on how much labor and capital is going to be used. So very important, you should note that the slope of this ISO cost line, it is a straight line, so the slope is going to be constant. So let's look at the next figure, 7.6a. So that is the top part of this figure. So here you can see we've got 3 ISO quants. We have 3 ISO quants. The first one gives you an output of 100 units, although it's not displayed clearly there. The second isoquant gives you 200 units, and the third isoquant gives you 300 units of output, respectively. And then there are also 3 ISO cost lines. This first ISO cost line is an ISO cost line where C is equal to $1,000. Here, the second ISO cost line, C is equal to $2,000, and the third ISO cost line, C is equal to $3,000. So, having a look at the information that we are given, we can see that points A, B, and C are the cost minimizing points. That is the points of tangency for each ISO cost and ISO quant curve, respectively. So let's say we look at our third ISO cost and ISO quant line to produce an output of 300 units given by this ISO quant line. The lowest cost to produce those 300 units would be given by this ISO cost line where C is equal to 3,000. So at point C, you have that point of tangency, and the input combinations of capital and labor to yield an output of 300 units in that lowest cost manner. It would require 75 units of capital and 150 units of labor. If we have a look at the second ISO quant and ISO cost line, if we want an output of 200 units for it to be produced in the lowest cost manner or in a cost minimizing manner, the input combination of capital and labor would be 50 units of capital and 100 units of labor, respectively, to obtain an output of 200 units on the ISO cost line, where the ISO cost line is equal to $2,000. So at that point, that is the cost minimizing point, with the combinations of inputs being 50 and 100 units respectively. Now take note of the curve going through the origin through points A, B, and C. This is called the expansion path. Now, the expansion path from the origin through points A, B, and C, it is going to show us the lowest cost combination of labor and capital that can be used to produce each level of output in the long run in that lowest cost combination way when both inputs can be varied. Remember, in the long run, both inputs can be varied. So notice that your expansion path here is upward sloping. And if you wanted to calculate the slope is going to be equal to a half. That is given by your change in capital 50 minus 250 over 100 minus 50. That would give you a change in K over your change in R, and that gives you the slope of your expansion path. It's positive because it's upward sloping and the slope is a half. Now, from the expansion path, the firm's long run total cost curve can also be derived, and the following steps need to be followed. So I'm going to go back to the previous slide. So the following three steps need to be followed in order to derive your long run total cost curve. So the first step is, if you want to move from your expansion path, which is that curve that went through points A, B, and C, if you want to move from your expansion path to your cost curve, the first thing you need to do is choose an output level represented by an isoquant, right? And then find the point of tangency of that isoquant with an isocost line. That should be easy enough. Then from the chosen isocost line, determine the minimum cost of producing that output level that was selected. And then you need to graph the output cost combination. So we are returning to figure 7.6a, but now in particular, we are going to look at part B of the figure. Now in part B, we can see the output cost combinations that are plotted. So on the vertical axis, you've got cost, and on your horizontal axis, you have output, hence output cost combinations. And if we look at points D, E, and F, they correspond to points A, B, and C respectively. So if you have a look at point D corresponds to point A. That was where the point of tangency occurred, and we had an output of 100 units. And the lowest cost combination of the inputs were given by 25 and 50 units of capital and labor respectively, and that came at a cost of $1,000, as we can see here by our coordinate on our vertical intercept. Then if we look at point E, that corresponds to point B, where we had 200 units of output, and that cost was given by the isocost line, where it was $2,000 as well. And then lastly, point F corresponds to point C, where we had 300 units of output, and that came with a cost of $3,000, as we can see. So in part B, what we have plotted is the corresponding long run total cost curve from the origin through points D, E, and F that measures the least cost of producing each level of output. Now, slides 26 and 27 is for knowledge enrichment purposes. Please work through this example to enhance your understanding. We continue with section 7.4, which deals with the long run cost curves versus your short run cost curves. Now, figure 7.8 allows us to explain the inflexibility of short run production. So you know, in the long run, all inputs are variable, but in the short run, not all inputs are variable. As we know, in our case, capital was regarded as fixed in the short run. So in terms of how we've plotted it, we have capital on the vertical axis, and you can see it is capital per year, and labor is on the horizontal axis, and it is given as labor per year. Now you will see the long run expansion path goes from the origin, and it is a straight line in this case, and it is the same as what you had from figure 7.6. However, in the short run, the expansion path is different, and let's understand why. So in our example here, in the short run, capital is going to be fixed at K1. And Q1, the output Q1, can be produced with the combinations of the two inputs K1 and L1, and that is a point on the isocost line AB. So this is the cost minimizing combination of the two inputs K1 and L1 that will produce this output Q1. Now, if you wanted to expand output from Q1 to Q2, in the short run, that could only occur as a result of your labor input increasing. So that would increase from L1 to L3, because remember, capital is fixed at K1 in the short run. So then you would find yourself at point P on isocost E if, and then output Q2 can be achieved in the short run, but as I said, it came about as a result of your labor input increasing between L1 and L3 because K1 was fixed. So therefore, your short run expansion path follows from the origin through to K1, but at K1 being fixed, your short run expansion path then becomes a horizontal line. Now, in the long run, Q2 could be produced at this point of tangency where you have your isocost line CD being tangent to your isoquant line Q2 at this particular point. And at that point, your combination of inputs are K2 and L2. And remember, in the long run, you were able to vary capital. So that is why you are able to choose this combination of K2 and L2. And this represents a cost minimizing combination of these two inputs to yield this output Q2. So now your long run expansion path traces through these 2 points of tangency. So, in the long run, the cost of producing can be minimized because of being able to substitute one input for another if it is cheaper. And the firm can produce at a lower average cost. We can see that in that CD was a lower ISO cost curve than EF. So, in the long run, there can be a lower average cost. Now, in the long run, the ability to change the amount of capital allows for the firm to reduce costs. And the most important determinant of the shape of your long run average and marginal cost curves is the relationship between the scale of the firm's operation, so increasing, decreasing constant returns to scale, and the inputs that are required to minimize costs. So, for instance, if you had increasing returns to scale, a doubling of inputs would result in output more than doubling. So, average cost of production falls with output. Cost was doubled, but output more than doubled. So, here you can apply the same reasoning to decreasing returns to scale as well. The following 3 bullet points just explains what these curves pertain to, and then on slide 30, figure 7.9 shows these curves and the relationship with one another. So now your long run average cost curve, you know what average cost means. So for your long run average cost, it's a curve that's going to relate average cost of production to output when all inputs are variable, right? Because we're speaking about the long run. Whereas your short run average cost curve, it's going to be a curve that is relating average cost of production to output when capital is fixed. And then lastly, your marginal cost curve in the long run, it's going to show a change in your long run total cost as output is increased by 1 unit, hence that marginal aspect of the definition. We'll continue with figure 7.9.